In Laplace transform, we are going to see initial value theorem and final value theorems. For the initial value theorem, shortly IFT. Limit t tends to 0, f of t equal to limit s tends to infinity s of phi of s. This is called initial value theorem. Again, final value theorem. IVT, FVT, final value theorem. This is t tends to infinity, f of t equal to limit s tends to 0, s of phi of s. This is called final value theorem. Initial value theorem, final value theorem. Here, L of f of t equal to function of s. We know already. If they give f of t, we should find function of s. If they give phi of s, we have to find f function of f of t. This is L inverse of phi of s. But if they give f of t, we should find phi of x. If they give f of t, we find phi of. If they give f of t, we should find. If they give phi of s, we should find phi f of t. If they give f of t, we should find phi of s. Here s is extra. Here t infinity, here t 0, here t infinity. S tends to 0, here s tends to infinity, s tends to 0. S is extra at both these places. First, let us derive how the initial value theorem and final value theorem, these limits formed. It is from the transforms of derivative. We are going to, from the beginning, how these two theorems formed. Let us go into transforms of derivatives. Transforms of derivatives. We already seen. Now again we are seeing to find the proof for initial value theorem and final value theorem. L of f of t. Dash means one time differentiated. Function of t is one time differentiation. This is called a dash. Equal to 0 to infinity e power minus st f dash of t dt. In general, Laplace transform, L of f of t equal to 0 to infinity e power minus st f of t dt. Whatever comes in L, it comes in the integral. Integral mark e power minus st dt are permanent. We are integrating with respect to t only. S is other than t. Therefore, result will be function of s. This will be function of s. This is just Laplace transform of f of t. Here, Laplace transform of differentiated function. F of t is differentiated one time with respect to t. This is called f dash of t. We are giving Laplace transform. This is called transform of derivatives. At the right, we are going to use integration by parts. Integration by parts. This is u dv equal to uv minus integration of v du. This is called integration by parts. Let us compare this left side. U equal to differentiable easily e power minus st, which is differentiable. We are taking u. This is integrable. dv equal to u dv. U dv. Here dv equal to f dash of t dt. Let us give space. dv equal to f dash of t dt. Here du comes, we have to differentiate. Du equal to e power minus st. We are differentiating with respect to t only. Coefficient minus s. Therefore, minus s chain rule dt minus s into e power minus st dt. This is du. dv is this. We have to integrate v equal to dash means differentiate function. If we integrate, we will get f of t. Differentiate function. If you integrate this, we will get f of t. All these four we are applying at the right side of the integration by parts. U e power minus st. V f of t. Limit we have to apply 0 to infinity. Minus 0 to infinity v du. V is f of t. Du is minus s e power minus st dt. Equal to e power minus st f of t. Limit is 0 to infinity. Let us bring this negative out. It comes as positive. We are integrating with respect to t only. Therefore, s is other than t. It will come out as a constant. And 0 to infinity e power minus st f of t dt. Now apply upper lower limits. Upper limit infinity e power minus infinity is 0. We must know we just infinity is infinity. We are minus infinity is 0. E power only infinity is infinity. Therefore, upper limit is e power minus infinity 0. Let us put 0. If 0 comes, completely 0. Whatever the function f of t may be. Minus lower limit 0. e power 0. When t is 0, we are putting e power 0. T also 0. F of 0 plus s into, see, we know 0 to infinity, L of f of t equal to 0 to infinity e power minus st f of t dt. 0 to infinity e power minus st f of t dt. It will become L of f of t. Again, e plus 0 is 1 minus f of 0 plus s into L of f of t. Again, s of L of f of t minus f of 0. In the left, we know L of f dash of t equal to s L of f of t minus f of 0. See, L of f of t equal to, we have seen initially function of s. Therefore, this is the transform of derivative. First derivative, transform derivative. Let us giving the shape, same 0 to infinity e power minus st f dash of t dt. Whatever comes in L, this comes into integral. These are all permanent. Integral mark e power minus st dt are permanent, equal to s into L of f of t is function of s. Function of s minus f of 0. Taking both sides limit, s tends to infinity. Limit s tends to infinity on both sides. 0 to infinity e power minus st f dash of t dt equal to limit s tends to infinity s of phi of s minus f of 0. We are integrating with respect to t only. This limit enters into integral. Therefore, 0 to infinity limit s tends to infinity e power minus st f dash of t dt equal to limit s tends to infinity s of phi of s minus f of 0. See, if you give infinity for s, it will give e power minus infinity. E power minus infinity is 0. Just we have seen already. Therefore, the entirely will become 0, equal to limit s tends to infinity s of phi of s minus f of 0. This f of 0 comes to the left. F of 0 equal to limit s tends to infinity s of phi of s. Here f of 0, wherever t comes, we have already put 0. Therefore, again, this can be written as t tends to 0 f of t equal to limit s tends to infinity s of function of s. This is called initial value theorem. Here 0 comes, therefore we are writing limit at the side, limit t tends to 0 f of t. If you put limit, f of 0 will come, the same will come. Therefore this is the initial value theorem, IVT, initial value theorem. Again we are going to see final value theorem. Again we are writing same term sums of derivatives. 0 to infinity e power minus st f dash of t. Let us write from the beginning. L of f dash of t equal to s of phi of s, s of L of t minus f of 0. This is we have written already, e power minus st f dash of t dt from the basic. Yes, this is L of f of t is phi of s, just we have seen, which is f of 0. In this line, we should take limit for s. S tends to 0. Let us take both sides. Limit s tends to 0. Limit s tends to 0, 0 to infinity, e power minus st f dash of t dt equal to limit s tends to 0 s of phi of s minus f of 0. This limit enters into the integral. 0 to infinity limit s tends to 0 e power minus st f dash of t dt equal to limit s tends to 0 s of phi of s minus f of 0. S tends to 0. If you give 0, e power 0 is 1. E power 0 equal to 1. Therefore, 0 to infinity 1 f dash of t dt limit s tends to 0, 0 to infinity, s tends to 0, s of phi of s minus f of 0. This is already differentiated function. If you integrate, we will get f of t only. Limit is the same, 0 to infinity. Just f dash type is there. If you integrate f of t, limit is the same, equal to limit s tends to 0, s of phi of s minus f of 0. Giving upper limit f of infinity, applying for t, f of infinity is infinity, minus lower limit 0, f of 0 equal to limit s tends to 0, s of phi of s minus f of 0. See, negative of 0, negative of 0. 2 get cancelled. Remaining is f of infinity equal to limit s tends to 0, s of phi of s. Here infinity for t. Infinity comes for t. Therefore, we can write as a limit form t tends to infinity f of t. Instead of t, we are writing infinity, infinity. Coming reverse. Limit s tends to 0, s of phi of s. This is called final value theorem. Hence a proof.